Differentiability. So differentiability is to f prime what continuity is to f. And essentially a function f is differentiable at a if f prime exists at a. And that's pretty much saying the same thing as the graph of f has a non-vertical tangent line at a. Because the derivative is the same as the slope of the tangent line, and so what you need is a tangent line to exist that's not vertical. And there are three ways to not be differentiable. The first is if your tangent line is vertical. And how that makes sense is if the tangent line is vertical, then the tangent line has an undefined slope, because vertical lines have an undefined slope. And if the slope of the tangent line is undefined, that means the derivative is undefined. A go-to example of this is f of x equals x to the 1/3, the cube root function. At the origin, the tangent line is vertical. And in some more formal terms using limits, this means that the limit as x approaches a from the right or the left side of the slope, this is the difference quotient that gives us slope, whose limit gives us the derivative. This limit is either positive or negative infinity. So essentially, that limit right there is called a one-sided derivative. If it was just the limit as x approaches a, that's the derivative, but from the right or the left is the one-sided derivative. And this means that the derivative from one of the sides is going to infinity, which is not a number, so f prime does not exist. The second way is a cusp or a sharp point at x equals a. For example, the absolute value function, which has that v shape, or x to the 2/3, which has that kind of like stick figure bird shape, if that's a thing. It's similar to the vertical tangent line. It's the one-sided derivative does not match the other side. So the left side slope does not match the right side slope. Like there isn't a smooth change. For example, a polynomial has all smooth lines. Make that one extra smooth. So there's a smooth transition of the slopes. It never just changes abruptly. It always just kind of like levels off and changes. Down here, the slope changes abruptly. There is no smooth transition from this negative slope to that positive slope. So the left-hand slope does not match the right-hand slope. That gives you a cusp or a sharp point. And again, this is the left side derivative, and that one is the right side derivative. The third way to lose continuity is if you are, the third way to lose differentiability is if you lose continuity at the point. For example, a piecewise function might do this. Let's take into account this piecewise function right here. So it's a piecewise function, and even if the left-hand slope is the same as the right-hand slope, even if that is the case, the fact that you lose continuity is enough to lose differentiability. Because essentially it's like, where does the tangent line go? There's not just one point on your curve there. And since the derivative is a limit, you need the right and the left sides to all match up. So if you lose continuity, then you lose differentiability right off the bat. So any break in continuity is also a break in differentiability. As an example, let's check out this piecewise function. We want to find a and b to make this function differentiable for all real numbers. Looks like I forgot to actually finish the question. I'll say differentiable everywhere, which means all points on the real line we have differentiability. So you want to find a and b to make that so. If you want to try it on your own first, feel free to pause and then turn it back on once you're ready to see the answer. Okay, so the answer. So we need two things here. We need differentiability, of course, which means the left-hand slope matches the right-hand slope. And we also need continuity, because as we just saw in the third condition, you need continuity to have differentiability. Now, both these functions are polynomials. Polynomials have no issues anywhere. So for the entire domain of the cubic function, there's no issues with differentiability. And likewise for the entire domain of our quadratic. The only possible issue is 2. 2 is where the switch happens. So again, there's no issues on their domains, so no need to consider their domains. The only point we care about is x equals 2. And we care about 2 things. We care about continuity, and we care about differentiability. Continuity means that these 2 equations will match up at x equals 2. So we need ax cubed to equal x squared plus b at x equals 2. Plug 2 into those equations, you get 8a equals 4 plus b. Differentiability, we differentiate our piecewise function to give us 3ax squared for x less than 2 and 2x for x greater than 2. And in order for our function to be differentiable for all x, we need the left-hand slope to match the right-hand slope. And so what we need is 3ax squared to equal 2x at x equals 2. So we plug 2 into that. It gives us 12a equals 4. A is a third. Plug the 1/3 into this equation over here. 8/3 equals 4 plus b. B is negative 4/3. And there we have it. With those 2 values of a and b, we have a function that has no issues with differentiability on the entire real number line. And if you were to graph this in Desmos, for example, you could put the a and the b into it and play around with different values of a and b. You see that when you have these 2 values, there's a completely smooth transition in your graph from the cubic to the quadratic. Like the graph just looks like this. From the graph alone, you can't even tell it's piecewise. That's because differentiability is the same as being smooth. Because there's no sharp points, no breaks in continuity, everything is smooth. So a differentiable function, if it's piecewise, you can't tell where the piece, or like where this piece ends and that one starts. Because that's smooth change. So a differentiable curve is smooth. And just to recap, we only had to examine x equals 2 because neither of these 2 functions had any issues on their domains. If like we changed it a bit, if say the second function was like 1 over x minus 1, I actually call it x minus 10. Now we know that we lose continuity at 10, so we also lose differentiability at 10. But we didn't have to consider that because our function was a polynomial.